All right, guys, how's everyone doing?
Good.
Good, how
Excellent.
are you?
Good to hear. I'm doing well. All right, so yesterday I said we are gonna do plate tectonics. Well, that was a lie. We're gonna do geologic time instead. Um, that'll be a better choice rather than jumping into plate tectonics. A lot of the stuff that we study in plate tectonics will come out of talking about geologic time and how we date rocks and how we know how old certain rocks are. So we're gonna start with that. Um, hopefully all of you have seen that the Canvas site for, excuse me, the lab is finally up. Sorry about the delay. We had a lot of problems with, number one, getting TAs covered for those classes. Not entirely sure why we had such problems with that, but that should be all taken care of now. And any questions that you have about lab, just direct it to your TA. If he has any problems with whatever whatever's going on in lab, he'll talk to me as well, so we can work out any issues that come up. All right, so let's talk about geologic time. So just a little bit of history about studying geologic time and how Earth is shaped and formed. People have been thinking about this for quite some time, going back to the Greek philosophers, Aristotle, Pliny the Elder. These guys, they were, being a philosopher meant that you were supported by the state to just think about things and think about how things worked. So Aristotle was the first one to suggest that Earth changes at very, very slow rates, which is something that is absolutely true, and that is that we've come to realize the more we understand about Earth itself. Pliny the Elder was the first to understand that amber is a fossil. It's encasing some type of biotic material in a greater solid. So he was the first one to understand truly that fossilization is the key to understanding the past and how we interact with the world that we see. Ibn Sina was he was a Persian polymath from Tehran, part of the Islamic Golden Age, where cities such as Tehran and Baghdad were undergoing great scientific breakthroughs. They're the reason why we use Arabic numerals for our numbers from 0 to 9. They're the reason that we have algebra, algorithm. Those are Arabic words, and that all stems from the Islamic Golden Age. So he was the first one to study earthquakes, water sources, landscape diversity. He was really one of the greatest minds of his age. And then we get to Shen Kuo, who was one of my heroes. He formulated the first theory of geomorphology, what I study, which is the way landscapes change. He observed mountains and weathering processes in China. He saw those tumbling rocks falling down the mountain. Those rocks would then enter the waterways, the rivers, and then be transported elsewhere. So he was the first one to really understand that Earth is always constantly changing and moving and restructuring itself. So then we get to James Ussher, who he was a priest, but he also had an academic career at Trinity College. So he wanted to figure out how old the Earth actually was. So because he was a priest with the Catholic Church, he was very influenced by the Bible. So he used the Bible as a way to kind of like a roadmap to figure out that the Earth was exactly 6,000 years old and creation occurred on exactly 6 p.m., October 22nd at 4004 BCE. Obviously, this is not the case, but this does create a conundrum for people studying after him because this was pretty much set in stone by the church. They thought that the Earth was 6,000 years old. How could we have so much change in 6,000 years? How could we have volcanic ranges, mountain ranges, big oceans opening up, large bodies of water? How could we have great vast canyons on the Earth's surface just in 6,000 years? So enter James Cuvier and catastrophism. James Cuvier was, George Cuvier, I misspoke, mixing up James Hutton and George Cuvier. So he was the proponent of catastrophism, which is the idea that all of Earth's features were caused by these big, violent, sudden catastrophes, these big events that aren't related to each other. They just happen, and then they form all of these different features that we see today. He was also a fossil record expert. He correlated things like elephant fossils that ended up being mastodon fossils. And he was the first one to suggest that Earth was at one point dominated by reptiles. So he was the first one to understand that there was an age where dinosaurs were king. So now we start to get to the Enlightenment period where people are actually starting to think scientifically. Rather than thinking about catastrophism as just a whole and as a really simple explanation for everything. James Hutton, who was a Scotsman, part of the Scottish Enlightenment. He was with the same Enlightenment thinkers such as David Hume, who founded the idea of utilitarianism. If any of you are unfamiliar with what that is, it's about everything should be done for the happiness of people and the greater good. It's a really interesting philosophy, as well as Adam Smith, who is the founder of the writer of The Wealth of Nations. He created the idea of the free market. So this is where a lot of the overall societal changes are going on is in Scotland at this time. It's a really interesting time period to read about. But he was a scientist and he was a geologist that just observed things that he saw around him. He was very interested in this area right that you see on the right. This is called Sicker Point. And the one thing he noticed was that the rocks seem to be organized into layers, but they're at different angles. So what would cause that to happen? Why would they ever be in that orientation, and why would that be so different? He also looked at different ripple marks in different sandstones. He observed ripple marks caused by wind on the beaches of Scotland, and then he correlated those to ripple marks that he saw in rock formations. So he thought, maybe there's something to this. Maybe these things happen at very slow rates, and maybe it's always happening. So if we orient these this way, then we get pretty much the same thing. So he came up with the idea of uniformitarianism, where this key geologic theory where the present is the key to the past. The same things that are happening on Earth today happened 1,000 years ago, happened 10,000 years ago, happened several million years ago. So if we can understand what's going on today, we can understand what happened in the past and vice versa. So by studying these things, we can understand how things worked. So James Hutton really developed this from similar to Shen Kuo, where he observed weathering processes in Scottish mountains that would fall down the mountain slope due to gravity. They would eventually fall into streams and be carried downstream. And eventually those layers of sediment that get deposited, and then they get lithified and they form new sediments. So based on uniformitarianism, if things are happening at such a slow rate, that means the Earth is not 6,000 years old. It means it's really, really, really old. So billions of years old. The Earth that we live on right now is 4.6 billion years old. That's when it started to form. There's a lot of cosmic dust and rocks that just merged together, and a lot of cosmic bombardments that ended up forming this rocky planet that we call home. So something that geologists do frequently to understand the time scales that we're working with millions and billions of years. So it's really hard to visualize. So what we do is we put it on a calendar year. So if the beginning of the Earth is January 1st and today is midnight of December 31st, everything within geologic time falls on that 1 year calendar. So if this is the case, then the Hadean eon goes from the beginning of the year until like February 10th. You got the Archean from the 10th till the middle of summer. You've got the beginnings of life around June, going up through November. The dinosaurs would be dominant in mid-December, but they would be extinct on December 26th, right after Christmas. Modern humans would be showing up probably around 23 minutes to midnight. And then James Hutton found his ideas of uniformitarianism 1.5 seconds ago compared to today. So that's the kind of timescales that we're working with. They're very large, and geologic timescales happen very slowly. So whenever we're talking about things, we're working with thousands of years, millions of years, billions of years. So anytime you're trying to visualize geologic time, try to think of this time scale. So this is a very good tool to have to think of how long things have been going on. So this is the simplified geologic time scale. So it's broken into eons, eras, periods, and epochs. They're each broken down by certain events, certain significant maybe extinction events. Maybe there was a shift in the biodiversity. Maybe there was a shift in the atmosphere. But they're classified based on a number of scientific parameters, which we'll go over. So eons are the largest and longest periods of time. Epochs are the shortest. So if we were going from older to younger, from the Hadean eon to the Phanerozoic eon, which eon are we in right now? Go ahead and type your answer in the chat. All right, you guys look like you know what you're talking about. That's exactly right. We're in the Phanerozoic eon, which is pretty much where everything important that we know of is really happening. Most of life on Earth happened during the Phanerozoic, and of course we live in the Phanerozoic still. So if we're in the Phanerozoic eon, what era are we in? Go ahead and type your answer in the chat again. Exactly. We're in the Cenozoic. Very good. B. So this is where we get the rise of mammals in the Cenozoic. The Mesozoic was where dinosaurs roamed the Earth. Now, what period are we in? Same thing. Very good. We're in the Quaternary. The Quaternary is defined by glaciers and glacial periods. So during the Pleistocene, we had these big glacial events that carved out a lot of the Appalachian Mountains, that carved out most of the Great Lakes. A lot of the glacial features that you see in the northern states and Canada, that happened during the Quaternary period. And then finally, what epoch are we in? I'm not going to make you guys type it in again. You guys probably have figured it out. We're in the Holocene. The Holocene started about 10,000 years ago. 12,000 years ago, close enough. That was when the last glacial maximum was in North America, meaning that was the last glacial advance. And ever since then, we've never had so many glaciers on Earth. And a lot of scientists are starting to think that we're in a new era or epoch called the Anthropocene, just because of how much influence that human beings as a whole are having on the geologic record. We're building things, we're digging things out, we're mining, we're dredging, we're changing the landscape, we're changing the rock surfaces, we're weathering things using machinery. So a lot of geologists think that we're in a very new geologic time period. So let's talk about the beginning of the Earth. So in the early Earth, it wouldn't have been a great place to live. We call it the Hadean Eon. It's named after Hades, god of the dead in Greek mythology. Just a really hell on earth kind of experience. Massive volcanism, just everything still starting to form, very, very hot, very fresh, very new. So there's a lot of friction. You had a lot of cosmic bombardment. So Earth was just covered in these impact craters. Also, you have a lot of heat generated from radioactive decay. As atoms age, they break down into daughter atoms, and that breakdown produces heat and energy. It's what ends up heating the main source of energy from nuclear energy, which is why we have nuclear power plants. So we have no oxygen in this as of yet. We have a lot of CO2 sometimes as the rocks are breaking down and there are volcanic eruptions, there's outgassing. Those are going to end up sending gases into the atmosphere eventually. So the reason we know that Earth is roughly 4.6 billion years old is because of the oldest minerals on Earth that we've found. These are from the Jack Hills area of Australia. These are zircons, and they have based on looking at the half-life of lead in these zircons, we could figure out that Earth is at least 4.6 billion years old. This has taken a long time. These are the oldest minerals on Earth. They're kept in a museum in Australia. Have not seen them yet. I've been really meaning to go and see them. They're really cool. Just to think that we have something that old and think of what it's seen. So now we get to the Archean Eon. Now we're starting to somewhat get a very primitive form of life on Earth. Some of these forms of life use photosynthesis. You're familiar with photosynthesis, getting energy from the sun, getting energy from CO2 and water, breaking that down to sugars and outgassing oxygen. So the photosynthetic organisms, that's where the source of oxygen that we're going to end up populating the atmosphere with comes from. These come from stromatolites. Stromatolites are these large algal mats. They're bacterial mats, and you can still see them in the fossil record. Actually, since I'm home, I have a stromatolite in my office. I'll grab it at the break and try to show you guys. But yeah, they form in these large algal mats. There are different types of stromatolites that form in these mounds that kind of look like bushes. And you can still see some of these off the south coast of Australia today. They still exist. Some of the oldest types of life on Earth. We also have chemosynthetic organisms. These you can find in some of the most uninhabitable places on the Earth. This is one of the acidic lakes in Yellowstone. If any of you have ever been there, it's a very cool place. This is where you're getting bacteria that gain their energy and caloric intake from breaking down chemicals such as hydrogen sulfide. And they break it down into sugars and water, as well as some sulfur left over. So these are the first forms of life forming in the Archean eon. So as we see here on this graph, if the right side of the graph is today, left side of the graph is 3.8 billion years ago, right around 2.5 billion years ago, we're starting to get some of that oxygen coming up, getting more and more oxygen in our atmosphere. We're building up an atmosphere that life can actually start to evolve and live in. So at the same time as we're getting more oxygen, we're developing more iron and reducing iron and oxidizing iron. And that iron ends up getting dissolved into a lot of these early oceans, these early acidified lakes, and they form in these like banded iron formations. They're very popular among geologists to study. There's a lot that we can learn from them about earlier times on Earth. As you can imagine, with the Hadean and Archean eons being so long ago, a lot of the geologic processes like mountain building, fracturing, faulting has broken down a lot of the formations that formed during that time. So we don't have a huge record of it. But when we do find the record of it, it's very valuable to study and find out as much as we can about it. All right, so now we're starting to get into more developed types of life on Earth, more multicellular organisms. So during the Proterozoic, we're getting some very, very more advanced forms of life. Not the algal mats, these are now starting to get mobile. We're still roughly 3 billion years ago, we're starting to get multicellular life. So this flat jellyfish type of looking thing is Dickinsonia. And this large leaf-like thing right here is the Charnia discus. Discus will help you identify the two. So these are filter feeders. They're not predators just yet, but they're filtering in water from these early oceans. And they're taking out all of this these small single-celled life forms that are existing in the water molecules, and they're taking them in and ingesting them. So this is how we're developing. All right, now we're going to get into the Cambrian. Cambrian is part of, now we're going to break this down into periods. The Cambrian is part of the Phanerozoic eon. So we're out of the Hadean, Archean, and Proterozoic. We're on the Phanerozoic, and now we're going to break into geologic periods. If you guys have any questions about this, sometimes this gets confusing with all the different time scales. Just shout out and let me know, interrupt me. I have a tendency to ramble, I'm sure you've noticed. So feel free to interrupt if you need some clarification.
Oh, sorry,
yes.
I was wondering if you can kind of go back to the last slide for like 1 second.
Yeah, sure.
I'm not explaining my question, but I'm kind of confused about like, I'm not sure if it's the speed of the lecture slides, but I'm kind of getting confused in like all the certain breakdowns of
Okay.
like different periods and like when the oxygen starts to like how it flows in and out of the environment at that point.
Okay. So let's go back to here. I think that what'll help is, okay. So if we're looking at, we're going to break it down by these eons and this time scale that we see here. So the problem with this graph is that it looks like it's scaled that the Phanerozoic is the greatest amount of time, and it's not. It's the Hadean, the Archean, and the Proterozoic all account for about 3 billion years of the first parts of Earth's history. So these are the biggest chunks of time it's not until around 1 billion years in the Proterozoic, 1 billion years ago from today, that we get life on Earth in those algal mats. Then we go into the Phanerozoic eon, which is from the Cambrian period to today. That's when we're getting more oxygen in the atmosphere. More oxygen in the atmosphere means that we're getting more oxygen in the oceans as well. And with that oxygen in the ocean, we're getting more advanced forms of life. Life that can take in oxygen, and life that can move, life that can see with its eyes, developing eyes and sensors. So this is where we're breaking it down. Is that helping? Does that make a little more sense?
Yeah, it does. Thank you.
Okay. Again, feel free to interrupt me. I'm not as good at teaching on Zoom as I am in person, so hopefully we can go back in person, because I think I'm a lot better with explaining things in front of an audience. But feel free to interrupt me and just let me know if something's confusing. Okay, so now we're in the Cambrian period, which is part of the Phanerozoic eon. The Cambrian period, we call it the Cambrian explosion because we get so many different types of life forms. We're not just getting those like jellyfish and those like leaf-like discs anymore. We're getting arthropods, we're getting trilobites like you see here, we're getting bivalves like clams and brachiopods. Excuse me. We're getting fungi, like early forms of fungus that form on the bottom of the ocean. We're getting so much different types of life, all because of this just random explosion of evolutionary periods. So during this time, we're developing the supercontinent of Pangaea as well. So the oceans are incredibly large and connected. So any oceanic life is just teeming and has more room to move around and develop. Life on Earth, on the land, is also developing as well. So during this time period, if you look at the late Paleozoic on the right, you could go from Delaware, you could take a maybe 20-minute train ride to West Africa if you wanted to. That's how smushed together we were. And obviously Africa is just almost a perfect puzzle piece into South America. That'll eventually rift apart. But this is what Pangaea looks like during this time. So from half a billion years ago to about 250 million years ago, we're developing and we're starting to rift Pangaea apart. All right, now let's move into the Ordovician era. Around 440 million years ago, we had a huge extinction event. Not the biggest, but a pretty big one. If we go back here, we can see a lot of life at this point is tropical. So all that life along the equator, it's used to a more warmer climate, tropical climate, a lot of rain, a lot of humidity, a lot of moisture. So that's what life is used to at that point. We think there was a big cooling event that basically killed off roughly 60% of marine species, marine genera, which means 80% of marine species disappear and we don't see it anymore. So this extinction event, that's what we're choosing as our boundary between the Ordovician period and the Silurian period. So now with our Silurian period, we get, with the deaths of other species, new species can kind of move in and take control and kind of explode in their own way. So we get development of eurypterids, which are also known as sea scorpions, which you see on the right. They can grow up to 36 feet long. Well, they could grow up to 36 feet long before they went extinct. So these guys were the kings of the ocean. You can also get crinoids. These, what we call in the geologic world is poker chips that you see on the left, these little stems. These are the segments of this, what's known as a sea lily, which we actually still have today. These have persisted, crinoids have still persisted from the Silurian to today. So you can still find them on the bottom of the ocean. Really cool little things. But this is where we develop new types of life, new types of filter feeders, new predators. So we're moving more into more developed types of life. So now we're in the Devonian, and just to bring it back to the United States, what the United States looked like at that point is a lot of it is underwater. Delaware is surprisingly more on land. The central US is on land, but there's this big seaway right through the center of it. And it's very, very tropical. This is where we start to develop the movement of animal species from the water to the land. So we also get some large fishes. We used to have jawless fishes. Now we have jawed fishes, like you see here with Dunkleosteus. You've probably seen at least a picture of this fossil before, really famous fossil. This thing is huge. It's almost 30 feet long, and it weighs the weight of roughly 3 cars. So it's a huge fish that reigns supreme during this time period where the oceans are running right through the middle of the United States. We're also getting the first amphibians. We're starting to get life that crawls out onto the land. Before, all we had on the land surface was just trees, plant life, pollinators, nothing that would really influence the landscape like animals. So we just have plant life on the terrestrial surface. So it starts with these types of lungfish that can jump from pond to pond by like kind of wriggling. It enables them to move to new places, enables them to find mates in new areas. Eventually, we're going to develop fish with rudimentary legs like Tiktaalik. Tiktaalik was discovered somewhat recently, probably like 20 years ago, and it was the missing link between fish and land animals properly. Tiktaalik couldn't really walk, but it could flop. So it could flop up on land. It could breathe. It had lungs, so it could breathe the atmospheric air. It didn't have to circulate anything through gills. And then jumping from Tiktaalik to Ichthyostega. Ichthyostega has proper arms and legs, has proper appendages, and it can actually move and walk on the surface. So now we're starting to get into land animals. Is this making sense to everyone so far?
Yes, sir.
Yeah.
Okay. I know this is a lot of information to throw at you, so I just want to keep track of everything. So now we're in the Carboniferous period, which is broken down into 2 different periods, which for our purposes, we'll just keep them the same as the Carboniferous. So now we're going to increase the oxygen. Trees are starting to just teem on the land surface, and they're just producing oxygen and oxygen and oxygen. An increase in the oxygen means that life on Earth can evolve and grow bigger and bigger. So with a 30% oxygen increase, we have 2 different supercontinents that'll eventually start to rift apart. America at the time is like a rainforest, very tropical. So we're getting just huge, vast forests of trees. We got a lot of mosses, very swampy, very humid. And this oxygen is going to enable land animals to grow even more and more. So the reason it's broken down into the Pennsylvanian and the Mississippian is this is where we get Well, we do get bugs. We start to develop insects, and because there's so much oxygen, these insects are huge. We're starting to get more and more development of these rainforests that eventually they die, they get buried, and whenever you bury these vast amounts of organic matter, you end up compressing it into coal. So all the Pennsylvania coal that exists in the northwest and northeast parts of the state all stem from these huge rainforests that eventually the trees start to fall over, they start to bury each other under sediments, and they just get compacted and compacted until you get nice anthracite coal that can power power our energy, power electricity, as well as used in the steel industry of Pennsylvania. So that's why it's known as the Pennsylvanian period, time period. So now we're in the late Paleozoic. We're finally getting back into the supercontinent Pangaea. We've started as these like separate different continents, and then we're smashing them all together at the end of the Paleozoic or the Permian. Now we're starting to get, life is just teeming all over Pangaea, in the oceans, everywhere. Now we're developing life more and more. And then at the end of the Permian, we are going to get the big one. The end Permian extinction is the biggest extinction event that we've ever seen in geologic history. 96% of all marine species, 70% of all terrestrial species. We call it the Great Dying for a reason. That's a lot of life on Earth that just disappears. The most likely reason is due to volcanic eruptions. There's an area in Siberia known as the Siberian Traps. I want you to imagine a volcanic province the size of probably New Jersey. Just imagine a volcanic fissure the size of New Jersey, just constantly erupting and sending gases into the air and ash. And it's just created this environment that was unlivable. The oceans became acidic, so that's the main reason for the extinction of marine species. Acidified oceans, they just can't survive in. It also dissolved a lot of oxygen into the oceans, so that was also a very big problem. So the main reason is the Siberian Traps, this huge volcanic eruption. Now, there's this theory out there that if you look on the exact opposite side of the globe from Siberia, in Antarctica, there is a crater buried way deep beneath the ice. They think that this crater had something to do with an meteorite impact that hit roughly around the same time. There's not enough information there, but it's enough that I should probably mention it. So huge volcanic eruption mixed with an impact crater on the other side of the globe, you're going to get a lot of death. So now that we're done with the Paleozoic period, now with the death of all those terrestrial species, you're going to get the age of reptiles. You're going to get dinosaurs coming into their own and existing. Because it was so much more hot and dry, reptiles were able to really adapt very well to that. They're cold-blooded animals, so they can adapt to that kind of environment. So we're starting to get the breakup of Pangaea. So during the Triassic, all the way through the Cretaceous, we're starting to those species that lived on this continent are going to end up getting separated. So you'll see in the fossil record similar stuff in South America as you would in West Africa, but then those that are still alive are going to evolve separately and in a different way, which we'll see a little later. So obviously this is the time of the dinosaurs. Fun fact, none of the dinosaurs in this picture existed at the same time. and not a single one of them existed in the Jurassic period, which is commonly misconstrued based on the fantastic film Jurassic Park. So during the Cretaceous period, which is the end of the Mesozoic period, we have a big ocean middle waterway, which was known as the Western Interior Seaway, all the way through North America, all the way from Mexico up through almost to Alaska. This is a huge body of water, and where we get things like mosasaurs, which are the predecessors of crocodiles and alligators. These very large amphibious, not amphibious. What's the word I'm looking for? Seafaring reptiles. Very big. A lot of cool stuff in the Western Interior Seaway. So at one point, the deserts of Nevada, Utah, Arizona were all underwater, which is crazy to think about. This is also ends up being part of Hudson Bay as well. Hudson Bay is an actual relic of this huge Western Interior Seaway. All right, so now we're at the end of the Cretaceous. We're going to get another extinction event, and this is probably the one that you know of, the one that killed the dinosaurs. So at the end of the Cretaceous event, the end of the Cretaceous period was a huge meteorite impact just off the Yucatan Peninsula in Mexico. This impact just caused huge dust clouds to cover the earth. Everything suddenly got a lot cooler. You're losing 75% of all plant and animal species. Because it gets cooler, dinosaurs are cold-blooded. They can't really survive that. So their prey starts to die off. Therefore, the predators start to die off. They can't handle the cold. So you end up getting more into the rise of mammals. So now we're developing different mammals, animals with fur, animals that can handle colder weather, that can reproduce without eggs. So they don't have to protect those eggs. So now we're getting into the age where we live. So at the same time, we're getting these huge mountain building events known as orogenies. An orogeny is an event that builds mountains. So the collisions of these continents that build up all of this rock. So for example, the Himalayas were developed from the continent of India. India used to be its own continent until it collided with the southern part of Asia, and it just kept going, and it's still going today, building up the Himalayas higher and higher. At roughly the same time, we have the Andes forming in South America along that strip of South America. You get the collision of this Nazca plate subducting underneath the South American plate. You get all these volcanic eruptions that eventually become the Andes Mountains. You also get the Alps in Europe forming from the collisions of Africa and the Saudi Arabian plate moving up into Europe. And earlier you get the buildup of the Rockies, all the way from the Sierra Nevadas up through Alaska, building up there too. So this is a huge mountain building event. In terms of us, the closest mountain range is the Appalachians. Those actually formed during the forming of Pangaea. So that's one of the oldest mountain ranges in the world. That's why it's so small, because it's been weathered so much, but it's one of the oldest mountain ranges in the world, whereas some of the biggest mountain ranges that we see today are a lot younger, so therefore they haven't had the time to weather down to the Appalachians' height. All right, so let's talk about the Quaternary period. This is where we get what's known as the real true ice age, which ends up killing a lot of the mammalian life, but we start to see the rise of humans, humans that can move to warmer climates, that can organize and develop agriculture, and get away from these heavily glaciated environments into areas where they can hunt, where they can cultivate. But during this time period, we see huge ice sheets from the northern hemisphere and the southern hemisphere, spreading all the way down as far as we've ever seen before. So I want you to imagine a glacier driving down right through New York City. That's how far these ice sheets were able to get with throughout this period because of how cold it was. So these ice sheets were huge and they just spread out so far. So that was a lot of information. We're going to take a 5-minute break. We'll meet back at, you know what, let's make it 10 minutes. Let's meet back at 11, and then we're going to talk about relative age dating. So go ahead and take a 10-minute break, and I'll see you guys in a bit. If anyone has any questions right now, feel free to let me know because I'll still be here. All right, guys. Welcome back. So I know there was a lot of information to throw at you in an hour. If you have any questions, please let me know. And if you're confused on any concepts, I'll do my best to help clarify. I also have office hours today from 4 to 5. If you need any help with anything, let me know. But I'll be available at office hours during that time. I should have sent you a Zoom link through Canvas. So if you do need any help, go to that Zoom link at that time. Also, if that time doesn't work for you, we can set up an appointment and we can work that out as well. But yeah, so second half of this lecture, we're going to be moving away from geologic time, but we're going to be talking about how do we establish how old things are in geology. So one of the early ways that we did this was through relative age dating. Dr. Wallace had a very good example to use. It's basically comparing things and judging which one is older than the other. So in the case on the left, it's obvious that Dr. Wallace is older than his daughter, clearly. On the example on the right, it's quite obvious that Dr. Wallace's father is a lot older than him. So basically, relative age dating is just which one is older than the other, which one is younger than the other. And even though that's a very simplified, blunt instrument in science, it's really helpful in establishing patterns and looking at the big picture of a rock formation or a geologic map or something of that type. So relative dating uses the same principles that all other geology uses. So we have the principle of original horizontality, which is everything is deposited in horizontal layers. The principle of superposition, which means that anything on the bottom is older than anything deposited on top of it. Principle of lateral continuity, which is just everything is deposited along these long flat lines until there's no more sediment or anything to deposit. And the principle of cross-cutting relationships, which is just the idea that if anything invades that layer, like a fault or a lava flow, that means that that thing that cross-cut it has to be younger than what was previously there. And we're going to break each of these down in tandem to make it a little simpler to understand. So horizontality, if you imagine sediment that comes from rivers. So let's see, sand gets stirred up in a river and then that river flows all the way to the ocean. Once it gets out to the ocean, stuff is not moving as fast as it was in a fast flowing river. So stuff starts to fall out of suspension. When it falls out of suspension, it falls in these horizontal layers. And it has to fall in these horizontal layers because if it didn't, it would flow to the bottom of wherever, and either way, it would be horizontal. So eventually you get these layers and layers of different sediments. Pressure and time, as we discussed last class, is going to compress that and lithify that into a rock that we can eventually, when it gets up to the surface, we can see and we can view. So for example, on this image to the right, we see all these layers in this ancient ocean. Eventually that ocean's going to dry out, that rock is going to be uplifted, and then rivers can cut through that rock and we can see each of those layers, which is exactly how the Grand Canyon formed actually. So these two examples are really great for looking at original horizontality. All of these are still in their original horizontal position. There's no deformation. You can clearly see the defined differences in the layers. And based on each of these layers, you can kind of start to see patterns in deposition. You can, like, for example, the sandstone and shale on the right from Cornwall, you can clearly see there's always sandstone and then a shale unit, and then sandstone and a shale unit. So it's always going to be alternating in that way. And that can tell us a lot about the environment that it was formed in. Okay, but it's very rare that we see these beautiful road cuts that are horizontal. Most of the time we see them in very different shapes and very different orientations. So what that tells us is that they always deposit in flat layers. If it deposits in flat layers and then we see it now and it is not in a flat layer, that means some type of force deformed or folded or faulted it. So that's one of the really basic inferences that we can make. Whatever force folded or faulted that originally horizontal thing had to happen sometime after those deposits were originally lithified. So we're getting back into relative dating. We know the deposits were made, and then a folding occurred. So one was older than the other. So this is, where is Sidling Hill? I feel like I've driven past it. I feel like it's in Western Pennsylvania. So this gives us a logical order of things, of course. So if you look at the layering, you can see it kind of has this concave shape along the road cut. Each of those layers had to be deposited in a horizontal fashion before it was then lithified into flat rocks. And then this huge folding event kind of created this bowl of these layers. And then eventually we cut the road through it, and now we can see these curved layers. So we know that the sediment first deposited, then they were lithified, and then they were folded by some maybe mountain building force, maybe tectonic force, something that folded these, some force exerted on these rocks. So the law of superposition, which is that older stuff has to be on the bottom, basically. This was developed by Nicholas Steno. He studied anatomy. He was also a priest. Way back in the day, a lot of priests were very interested in science, so they obviously coincided stuff. So he discovered fossilized shark teeth in rocks. And at first they were called tongue stones because they thought, well, there couldn't possibly be a way for the shark to put itself in the rock. It was impossible. So he came up with the idea of, why wouldn't it be easier for the shark teeth to settle in sediment and then that sediment be lithified, which means that the sediment has to be older than the shark tooth. So it's like, what came first, the chicken or the egg? In this case, the sediment had to be there first for the shark tooth to enter it. Conversely, it also has to be, everything had to be soft before it turned to stone, right? So everything had to be present in that rock before it turned into a rock. So that's the idea of superposition. What's older, and why is it that this specific thing is older? So the really basic part of this is, if something is going to deposit like a sediment, it has to deposit on some surface, some flat surface, right? So that means that, for example, if we look at these geologic formations on the right here, we know that the Kaibab limestone had to be deposited onto something solid, which means that the Toroweap formation was already lithified and stable at the time that the Kaibab was deposited on top of it. So that tells us that the Toroweap has to be older than the Kaibab. Same thing with the Coconino sandstone and the Toroweap formation. Coconino had to be lithified and stable for the Toroweap to deposit on top of it, and so on and so forth. So as you can imagine, everything below whatever formation is older than the formation above it. So the Supai group here at the bottom has to be the oldest that we can see on the surface. The Kaibab limestone has to be the youngest because everything below it had to be formed before it could be deposited. So basic rule of thumb, the youngest rocks are on the top, the oldest rocks are found on the bottom. Now this also doesn't just apply to sedimentary rocks, but also igneous rocks. If you think of Kilauea in Hawaii, all those massive lava flows that come out onto the fresh new rocks, that island already exists. There are lava flows that have made that island. So they're solidified, they're crystallized, they're stable. New lava flows deposit over top of them, and then those lava flows cool and recrystallize, and then new sediment and lava flows are deposited on top of those. So you end up getting these layerings of lava flows. You get ash beds that come in between because obviously volcanoes produce a lot of ash that eventually settles. So you can see these in igneous rocks as well as sedimentary rocks. All right, lateral continuity. Lateral continuity is just basically that anything that's deposited in that horizontal plane is going to continue to be deposited until there's no more sediment to deposit. So if you look at the image, you see that red, we'll call it clay. Yeah, we'll say there's this red clay that gets deposited in this area, and it keeps depositing until there's no more clay left from the river to deposit. And then eventually there's another sediment somewhere else. So those differences in the sediment can help us understand a little bit about the environment. But we know that that's going to be continuous in a horizontal flat layer from when it was deposited. Now, let's say those deposits get lithified. They're standing rocks now, and now we're going to run a river through it. And that river is going to cut right through that, almost like a knife. So in the bottom picture, a lot of geologic time has passed. That river has cut through that entire geologic formation, and a canyon has formed. But what we can do is, knowing that lateral continuity exists and knowing that the rocks haven't been folded yet, we know that the rocks on the left side correlate to the same types of rocks on the right side of the river. So that enables us to figure out which came first, which layer. If we don't have a good outcrop on the left side and maybe we see it on the right side, that can help us map things out. It also tells us that the river had to come after all of those rocks were deposited and formed and lithified, right? The river had to have something to cut through. So that tells us something as well. So this is a really good example. Because all of these layers deposit in flat, lateral, continuous layers, and these layers are very large, we can actually correlate rocks from 3 of the largest canyons in America. So Grand Canyon, Zion, and Bryce. And they're all in, Grand Canyon is in Arizona, Bryce and Zion are in Utah. Covers a very, very large area. But some of the same rocks in Bryce Canyon are found in Zion National Park. So if you look to the right, Bryce Canyon starts at the Wasatch Formation. It has several formations that were deposited during the Cretaceous and the Jurassic. And the Carmel and Navajo formations are the same formations found at the top of Zion National Park. So you can guess that Bryce Canyon is a younger canyon than Zion. It has more rock surfaces. It has more newer rocks. If you go down through Zion, we have the Carmel and Navajo sandstone. Keep going, keep going. Now we're into the Mancopi Formation and the Kaibab limestone. These 2 formations can also be found in the Grand Canyon. So these were deposited after the Grand Canyon. And then we can go all the way down to the base of the Colorado River and the Grand Canyon. So we can infer that the Grand Canyon is a much older canyon than Zion, and Zion is an older canyon than Bryce. Getting back into relative dating, which one is older than the other? So by correlating these different rock layers, we're able to tell a lot more about the landscape and how large these rock layers actually go. Does that make sense to everybody? All right. Okay, so we talked about how things deposit in horizontal positions and in continuous lateral horizontal positions. Whenever we find stuff that isn't horizontal and doesn't have straight lines, we can assume some change happens to that formation. So if we look at the top picture in figure C, we see number one, those horizontal layers have been uplifted and curved, but also we can infer that those layers would have continued if they were still there. Weathering has happened and it's cutting away at the rock, so all that's left is just this very irregular surface. Now we're going to deposit new stuff on top of that, and it's going to deposit, of course, in a horizontal layer. So if we see those horizontal layers right on top of some difference in angle, we can infer that the force that uplifted those rocks had to come before those new rocks deposited on top of the surface. So you get original rocks that form horizontally, you get uplift, you get erosion, and then you get new deposition. Does that make sense to everyone?
Yes.
Yes, okay. If it's confusing, let me know. And this goes back to what James Hutton was studying in Scotland. He saw these rocks at different angles. So he inferred that these rocks had to be deposited horizontally, some force tipped it over, and then new stuff was deposited on top of it. So this formation that's like almost vertical, that's Silurian. It's almost 435 million years old. The stuff on top of it is a lot younger, 370 million years old. So this was confirmed using absolute age dating, even though James Hutton, using relative age dating, could tell that the sandstone on top was younger than the mudstone on the bottom. So cross-cutting, sometimes you have these events that create some type of scar along the horizontal layers. So something that could happen is igneous features have what are known as dikes that kind of wedge their way through previous rocks, and they form these long deposits that cross-cut the older deposits. So something that we can infer about that is obviously those horizontal layers had to be there first for that layer to cross-cut through. So the cross-cutting layer has to be younger than the horizontal layers. All right, so let's take a look at this figure. So what's the relative, we're talking about the relative dating. So which one came first, second, third. So go ahead and type your answer into the chat. We have 1 at the bottom here. 4 is pointing to this black feature here, which is a dike, which is an igneous dike. 2 is this DOX formation, and 3 is this purple formation. So go ahead and look at the answers here. What's the correct relative dating sequence for the rock? We're going from oldest to youngest. Go ahead and type it into the chat. Okay, I'm seeing a lot of B. I see a couple of people with D. I see a couple C's. All right, so let's go through this together. So using law of superposition, is it the younger rocks on top or the younger rocks on the bottom? Younger on top. Very good. Okay, so we know 3 is not the oldest. That means that 2 is not the oldest either. So it probably makes sense that 1 is the oldest. Now, using cross-cutting relationships, now we're moving on to sections 2 and 4. So cross-cutting. So 4 is cross-cutting that unit 2 that we see. So which had to come first, unit 2 or unit 4? Two. Very good. So we have 1 being the oldest, 2 being the next oldest, and then 4. And then assumingly 3. So that means that the answer for this one is D. So does that make sense to everyone as to the workflow of that? Does anyone need any more help understanding that?
Yes, could you explain cross-cutting a little bit more?
Yeah, of course. So cross-cutting means that something basically went through this formation that already existed. So in this case, we have our 1 deposit here at the bottom. Then we have more deposits, the base deposit, the Hakatai deposit, the Shinumo deposit, the Dox deposit. Then we have, once those are deposited and they're lithified, then we have that igneous intrusion, that number 4, that dike come through it. Because since it's going through all of these formations, those formations had to exist before it went through them, right?
Right,
So,
okay.
yeah, so the layers have to exist for it to cut through. Now, that dike doesn't go through anything above that. So we can say that it's younger than 2, but it's definitely older than maybe these horizontal ones up top, the Tapiats, the Bright Angel, and it's definitely older than those ones. So we could, because it doesn't cut all the way through those, we know that it didn't get there. Does that make more sense?
Yes, thank you.
That's thanks for letting me know. We're gonna have a couple more exercises like this, and we'll have an in-class exercise that should help as well. All right, so that's relative dating. Now we're gonna talk about absolute dating. And absolute dating is done using the radioactive decay of atoms in rocks. So this is a picture of a graphite reactor. This is the type of reactor that's seen in a lot of nuclear power generators. Nuclear power is generated from radioactive elements that basically decay into new elements, and that decay generates heat and energy. And that heat and energy is used to heat up water, which turns into steam, which powers a turbine, and that ends up generating electricity. So that's how we've used radioactive decay to power cities, but we want to use radioactive decay to tell how old or young things are. So we can specify the number of years since a certain event occurred, but we still have an error. For very young deposits, less than 5,000 years old, we can use historical records for some of them. For example, in 1839, we know there was an eruption at Krakatoa because there were people there. They recorded it. They recorded ash flows. They recorded heat changes. Granted, it was from 1839, so it's not incredibly accurate, but we can tell pretty much down to the day when that eruption happened. For even older ones, like Pliny the Elder knew that Vesuvius erupted in 79 AD. He didn't note the time, the temperature, but we have at least a historical record of that geologic event. For anything older than that, we have to use radioactive decay. So radioactive decay is built on unstable isotopes. So we talked a little bit about isotopes and atoms in the last class. Basically, isotopes and unstable isotopes, they're transferring from a parent element to a daughter element through some type of decay. So over time, they'll eventually transfer different particles in their atoms into a daughter element, and that releases energy. So if we look at the image on the right, we have at the top of the image, we have lead-82. Lead-82 is its atomic number. Now, we are going to do beta radioactive decay on that lead-82. When we do this type of decay, we're actually turning one of the neutrons into a proton. So when we go from 82 protons to 83 protons, that changes its atomic number. Its atomic number goes to 83. So now we're at a different element entirely. It's now bismuth. And that change generates energy. So basically, whenever we're looking at a rock, we're seeing how many atoms in this certain rock sample have turned from its original element into its daughter elements. And that's how we establish how long something takes. Because this happens at a steady, constant rate, we're able to basically backtrack how long ago it started. Okay, so this is where half-life comes in, and you've probably heard this term before. It's the period of time over which the number of radioactive nuclei of the parent material have decreased by 1/2 into the daughter material. So looking at the graph to the side, if we just take a sample of 100 atoms, and at one point we have 100 atoms of the parent isotope. Over time, it's going to decay, and eventually half of those atoms are going to turn into the daughter product, whereas the other half are still at the parent product. So that's a half-life because we've gone from 100 atoms of parent to 50 of each. So that's the first half-life. Then we're going to do it again. We're going from 50-50 to 25 atoms of parent to 75 atoms of the daughter product. That's another one. That's the second half-life. So if we're able to calculate and count the number of half-lives, since this happens at a constant rate, we can establish the time that it is taken for those half-lives to take effect. So if we have this curve, if we have the blue curve on this graph is the parent atoms left, and the red curve is the daughter atoms that we've accumulated. So as you can imagine, with the fresh rock, we have 100% of the parent atoms remaining. Nothing has decayed yet at all. So as we go through time, the number of parent atoms decreases and the number of daughter atoms increases, as you can think of. So the first half-life is going to be 50% parent, 50% daughter. And then after that, we're going to accumulate more daughter than parent with 75 atoms of daughter, 25 atoms of parent. And then we're going to keep going, and we're just going to keep dividing by 2, basically, till 6 atoms of the parent remaining, and 87 and 94 atoms of the daughter remaining. So based on the number of half-lives, we're going to be able to tell the age of it. So after a lot of scientists have averaged these numbers out, we get a certain half-life value. So for uranium-238 decaying into lead-206, that takes about 4.5 billion years for half of the atoms of uranium to turn into lead. So if we look at 100 atoms and 50 of them are lead, that means that this has existed for 4.5 billion years. If we looked at it and we saw that 25 of those atoms were uranium and 75 were lead, that's 2 half-lives, which means that that is actually 9 billion years. So for each half-life, you just multiply it by its accepted half-life value, and that's the age that you're getting. So we can do this with a number of things because the half-life of uranium is so large, and because Earth itself is only 4.6 billion years old, it doesn't give us a lot of leeway in what we can study. So that's why we look at different isotopes. So carbon-14 is a pretty common one used by geologists. It's one of the shortest half-lives, 5,730 years. Because it's so short compared to geologic time, we can use this in dating bones from fossils, from even people, because people have been around for a few thousand years. We're able to see when or how long ago these people died or were at least buried. So potassium and argon has a half-life of 1.3 billion. That's useful for dating a little bit older rocks. So that's pretty helpful for us as well. Okay, so let's try this. I know this is a kind of confusing concept. So let's say we discover a lava flow and it has basalt in it, so we can date it using radiometric dating. So the sample that we have is 6% of the parent isotope. And the known half-life of this parent isotope is 200 million years. So we have basically out of 100 atoms, we have 6 atoms left of the parent. So who can tell me how many half-lives that is? Not the number of million years yet, but how many half-lives that is?
Four half-lives.
4 half-lives. Very good. Some of you have got the answer too. So if we have 4 half-lives with a half-life of 200 million years, we just multiply that by 4 and we get 800 million years. And that's how old our deposit is. So does that concept make sense to everyone?
Could you just go over where the 4 comes from again?
Where the 4 comes from? Sure. So we have the sample that contains 6% of the parent isotope. So if we have 6% of the parent isotope, that means if we had 100 atoms starting, we only have 6 atoms left. So if we look at this curve, right at 6 atoms left, that's the number of half-lives at 4. Do you see the line from the bottom?
Yeah, thank you.
Yeah. So that's where we get the number of half-lives. And if we know one half-life is 200 million years, then we can multiply each of those out. So if this question asked, we have 25% of the parent isotope left, what would that be?
400 million years.
Very good, exactly right. You guys are getting it. So does that make a lot more sense?
Yeah, thank you.
Yes.
Yeah, okay, perfect. All righty. Okay, so we're gonna go back. This is gonna be our in-class exercise that we're gonna work on together. There's also going to be an in-class assignment on Canvas for relative dating. It's gonna look a lot like this. You can do it over Canvas. I believe it is due the 8th. It should be open right now. So you'll complete that individually, but we're gonna go over this as a group right now, just to give you guys an idea. So let's say we have this sequence of features. So we have what looks like a really old igneous formation in H. Then we've got some sedimentary depositions from F through B. We have a fault in feature A, and G looks like a dike. I is the surface of the earth. Okay, so go ahead and type in the chat what you think the oldest formation is. Let's start with the oldest. All right, very good, very good. H is in fact the oldest. Okay, so going from there, what came first, F or G? F, very good. Okay. Now's the tricky part. Did A or G come first? Excellent. You guys are doing great. Because we can see that A has faulted all these layers. All these other layers from B to F are offset, but G is not offset, which means G had to come after the fault. Okay, so is everyone a little more clear on how to tell which came first in a figure such as this? Awesome. All right, so once again, there's a similar figure on Canvas. That'll be due the 8th. There's also quiz 1 is due at the end of the week, and that should be open. You should have 3 attempts with that. Your reading assessment 1 is also due tonight at midnight. So keep in mind, if you guys need any, if you have some trouble and you need an extension, just email me and let me know, and I'll accommodate you the best I can. I think that's it we have for today. So next week, tomorrow we're going to be talking about plate tectonics finally. And then after this week, next week is going to be more actual hazards, earthquakes, tsunamis. So I think that we're getting out of the weeds when it comes to all the background science of geology. So that'll be a lot easier and a lot more fun. But thanks, guys. Hope you have a great day. And if you need anything, let me know. I'll be in office hours from 4 to 5 tonight.
Thank you.
Thank
Have a
you.
good one.
Thank you.
If you don't mind. Can you kind of go over all the letters in the last slide just so I can like write it down so I can like use this kind of like a study guide for the.
Yeah, sure. Yeah, let's go over that together. So let me share the screen again.
I think I know it, but I think if I see the lay out it from you, I can be like, I can take it in my exercise and be like, oh, okay, like I know what it is.
Yeah, sure. So what I look for first is I usually go by which one is on the bottom, because that has to be one of the oldest. So that's why I think since H is on the bottom, everything has to be layered on top of it. H has to be the oldest, right? So then after that, I'm looking at the layers that are on top of it. So we have B, C, D, E, and F. Those are the sedimentary layers on top of H. So let's look at those layers and see what's going through them. So they're all horizontal, which means that B, out of those layers, B has to be the youngest, F has to be the oldest. Cutting through all of them, we have a fault, and we can tell it's a fault because they're offset from one another. And cutting through them also is G, this lava dike, which had to be this some igneous eruption that went through and cut through them. So we know if F is older than E, E is older than D, D is older than C, C is older than B. That fault had to cut through them, all of them at the same time, but they all had to be there before the fault. So the
Okay.
fault is younger than B, C, D, E, and F.
That makes sense.
So yeah, so that makes sense.
Yeah.
Okay, so that means that A is younger than B. Now, since we know that A cut through all of those and offset those formations, and we see that G hasn't been affected at all, and G actually goes through the fault, that means G is younger than A.
Okay.
Does that make sense?
Like kind of the only part I get confused on is when A is younger than B, I think you said.
Yes. So like B, so B had to be deposited in order to shift the way it did, right? So B was deposited flat, then the fault happened, and then it shifted down, right? So B has to be older than the fault. B has to be there before the fault can shift it down lower.
That makes sense. Okay.
Okay.
Okay. So what so you have H and then you have F, so you have F through B,
Yep.
and then it would be A and then G?
Exactly. That's
Okay.
right.
Yeah, that makes sense. Okay.
And if you're doing working on the in-class exercise as throughout the week, just let me know if you need any help, because it's a very similar thing.
Okay, thank you so much. Appreciate it.
Yep, my pleasure.
Have a good one.
You too. Stanislav, you need help with anything?